Volcanoes. Let's talk about them. With our discussion of volcanoes, we're going to talk the general terms involved with volcanoes. We're going to look at the plumbing underground to create these volcanoes. We're going to discuss specifically the magma involved because there are different types of magma and different types of volcanic environments. And then we're going to talk about those volcanic environments, specifically the tectonic zones that produce volcanic eruptions. Later, we'll talk about eruptive materials, eruptions, and the different types of volcanic landforms that result, because different types of landforms result in different types of magmas and different types of eruptions. And then the hazards involved with volcanoes to give you some examples. So here we go, starting with volcano terms. First off, we've got magma, and that's the term used to describe any kind of molten rock and melted minerals and crystals, all of them in a melt, gases, dissolved gases. That's magma, and that's what the term we use to describe molten rock underground. When rock is at or near the Earth's surface, we call it lava, but it's the same stuff. Magma and lava are the same thing. And then the actual opening of the Earth, of where the stuff comes out, that's called the vent, the volcanic vent. All right, so you often hear me use the term magma, but know that if it's at or near the Earth's surface, lava can also and probably should be used. Of course, we hear a lot about lava in Hawaii because a lot of volcanic activity is taking place in Hawaii, and they see lava on the surface. So lava creates lots of different rocks, but that's the general gist there. The term volcano then is what they describe as the materials that build up around the vent of the volcano. And of course, the more eruptive material, the larger the volcano. There are different types of volcanoes we're going to talk about that build up. A crater is a leftover divot from an eruption. Once you get the volcano built up, typically magma will pool up underground, and when it erupts, the magma comes on the surface and it leaves a space inside the earth, and that space drops down, typically gives you a little bit of a crater at the top of volcanoes. And caldera is a term used to describe a large crater. Okay, so you see pictured here a caldera, actually, and then a smaller volcano near and inside the caldera with a crater on top of it. And we'll talk about each of those. What creates volcanoes? Well, magma, and magma has certain plumbing that goes on underneath the surface. So let's talk about the plumbing of volcanoes. First off, there's a term called pluton, and a pluton is just a blob of rising magma. As magma rises through the crust, it kind of burns a path through the crust, often taking a path of least resistance through the rock. Perhaps there's a rock that melts easier than others. Perhaps there's some fractures in the rocks, but magma will typically follow these. Excuse me. And so plutons are blobs, and there are different types of plutons. There are sills, which are thin layers between rock layers. So magma will burn its way in between rock layers, maybe burn out that layer that's weaker or more easily melted. Laccoliths are where magma kind of pushes its way in between layers and rises or raises the layers above it up, create kind of a little bit of a dome above it. We talked about dome mountains, oftentimes formed by laccoliths. I remember the Black Hills and the Adirondack Mountains. And then dikes are intrusions of through angled fractures. And that's the term we use to describe any kind of magma that's burning its way through weaker fractures or existing fractures in the rock, sometimes even fault lines. And these are plutons, rising blobs of magma that burn their way through the Earth's crust. One more term, and that is batholith. Batholith is different than a pluton in that it is a huge, massive pocket of magma below the Earth's surface. Okay, so batholiths are greater than 100 square miles. They're larger than plutons. Typically, they're the main source of magma that rises up to form plutons. Batholiths oftentimes, through erosion, reach the surface, and so we can see these beautiful rock formations of igneous rocks. You see one pictured here. Oftentimes in mountains, in a mountain building, you'll see areas of batholiths. Let's talk about the magma. First off, how does magma get created? Well, obviously melting. Heat produces melting. As you get down deeper in the earth, about 100 meters down, the temperature can get up to over 1,000 degrees C. And so melting, of course, occurs in some of the rocks that have lower melting points, some of the crystals, rock crystals that have lower melting points. So as that heated magma rises through the crust, believe it or not, it brings that heat up more, and as it comes up more, there's less rock pushing down on it. There's less pressure, and so there's a thing called decompression melting, where when hot rock, begins kind of migrating upward due to its lower density, it'll actually melt the surrounding rock as it moves upward. And this is called decompression melting. So heat can cause magma to form, so can reduce pressure. And then water. As the magma rises through the crust, it also encounters areas of water. Groundwater can help the melting process. And then it's of note that when tectonic plates subduct at those subduction zones, the plate diving down into the mantle is waterlogged. It's been at the bottom of the ocean. And so that introduction of water to the mix of hot environment in the lower mantle, or sorry, in the lower crust and lithosphere, produces melting at a greater rate. And then when rocks with water in them melt, they're charged with that water vapor gas. The water turns into water vapor and produces a lot of gas in the magma. So typically at subduction zones, you have gas-charged magma that buoyantly rises through the crust. When it erupts, it explodes because that's trapped gas under pressure. Over 50% of the gases in volcanic eruptions are water vapor. So this shows a subducting slab. A zone of water release and heat produces magma where it forms, and it migrates up as plutons and creates plutons as it rises through. And of course, the buoyancy of that water vapor makes it get and reach the surface. There are a few different kinds of magma. There is so-called basaltic magma. And basaltic magma is usually dark colored because it's high in iron and magnesium. It's metal-rich magma. It's more dense because it comes from deeper in the mantle. Basaltic magma is mantle magma. As a result, it doesn't have a lot of that water vapor. It was not created from any kind of crustal melting, so it doesn't have a lot of gas in it. And the gases that are in it escape easily because the magma is pretty runny. There's a term called viscosity, and viscosity refers to the thickness of a magma. If a magma has a lot of viscosity, high viscosity, it's very thick. If it has a low viscosity, it's very thin. And basaltic magma, low viscosity, it's very thin. It's thin, it's hot, it's runny, it comes directly from the mantle. It's dense, high in iron and magnesium. This is the stuff that paves the ocean floor. And actually, the rock that's harvested to create our roadways, our asphalt, those are actually basalt pebbles. Yeah, Yeah, so right. So do you see this woman in the picture here? She's showing a picture, or she's probably photographing the lava flow here. First of all, it's really hard to get pretty close because this magma, or sorry, this lava is like 1300 degrees C. I mean, basaltic magma is hotter than the other types of magma. So you can't get too close. And secondly, um, it does run. Maybe melted ice cream would be a good analogy to how fast how liquidy this magma is. So if it comes in volume, yeah, and it's coming at a great speed, uh, the greatest speed would be probably as fast as you can walk. So it's probably not super dangerous as far as, but there has been some killer events. There was one killer event in 2002 where uh, the lava flow came through a refugee camp. There was a civil war in Rwanda, and there were some refugees in Zaire, I believe, and a lava flow came down the mountain from a volcano, and it trapped a bunch of people and killed, I think, like maybe around 100 or so of the people because of its fast-moving nature, and people just couldn't get out of the way. So there are rare events where this can be a thing. Rhyolitic magma is the second type of magma, and it is lower in density. It is rich in silica, and it comes from melted crust. It doesn't have as much iron and magnesium in it, so it's lighter in color. It has more elements like silica and potassium and aluminum and calcium. And so the minerals that are made are feldspars and quartz. They're pink and white and clear. There's also some black minerals that it makes, but they're more like flecks peppered within. If you've seen granite countertops, for example, you've seen the result of a rhyolitic magma cooling at a very slow rate. Rhyolitic magma is also called granitic magma in your textbook, and it forms granite when it has a chance to cool off slowly. Rhyolitic magma is sticky. It is more viscous, so it's thicker. It has more gas in it, typically because it comes from that melted crust. So it's very explosive. Okay. Whereas basaltic magma would be about the consistency of melted ice cream, rhyolitic magma would be like syrup or molasses in its consistency, even thicker in a lot of cases. You can use the term viscosity to refer to rocks as well. I've talked to you about how the rocks, quote unquote, flow in the asthenosphere. They're not melted completely, they're heated up at a great rate, and some rocks are more buoyant, they're just less dense than others. So even in a rock environment, rock will actually rise up through other rock. And this convection is what helps cause that movement in plate tectonics. So you don't think of rocks as viscous or being able to flow, quote unquote, flow, but they kind of do. And we also don't think of rocks as being elastic, but they are. And that's what causes that earthquake that release of elastic energy when rocks snap along fault lines. That's when they're colder or near the surface. They have a less tendency to flow and more tendency to bend and break because of the cooler temperatures and less overlying pressure. So basaltic magma and rhyolitic magma. I do want to mention that there is a intermediate of these two. Basaltic magma and rhyolitic magma are kind of the extremes. There is another one in between them. It's called andesitic magma. And andesitic magma, you might want to jot that down. Andesitic magma, like the Andes Mountains, it's actually named after that. Andesitic magma is very common along subduction zones, and that's where we get our big explosive volcanoes. Andesitic magma, Andesitic, andesitic magma. It's an intermediate variety of the two, intermediate style magma. It's directly from melted crust. It is more explosive. It's very similar to what you see here in rhyolitic magma, and it is typically found in the explosive volcanoes. So each of these magmas is actually found in tectonic zones. We talked about this already, that subduction zones are a main source of magma and eventual volcanoes. Subduction zones occur at plate boundaries, or excuse me, convergent plate boundaries. And as the crust, which is usually ocean crust, it's more waterlogged. It dives into the mantle of these subduction zones. And again, when it gets deeper in the earth, it hits that heat, and water mixing with heated crust makes it melt easier. And it forms that andesitic magma. Andesitic magma, as it burns through the crust, picks up more silica. It can become rhyolitic magma. Okay, so andesitic helps rhyolitic. Any kind of magma that burns through a lot of continental crust turns rhyolitic because it gathers a lot of silica through as it melts through the continental crust. So lots of silica, lots of water, andesitic and rhyolitic magmas. They form explosive volcanoes. And the explosive type of volcanoes are called stratovolcanoes. All the volcanoes that form along subduction zones are stratovolcanoes. And we'll talk more about those as we talk about the types of volcanoes next time. Two types of volcanoes form at subduction zones. Really the same kinds of volcanoes, just one form on the continents and one form from underneath the water. The ones that form along the edges of continents, those are called volcanic arc volcanoes. Volcanic arc volcanoes. I have a picture along South American coastline there, and the Andes Mountains are an example. All of those mountains are formed because there's a subduction of the Nazca plate underneath the South American plate. And that subduction zone, that oceanic crust diving underneath the continental crust, produces explosive volcanoes along the coastline. Explosive volcanoes along coastlines are called volcanic arcs. Oceanic continental convergence, volcanic arcs. Now, the picture in the lower right, I believe that's in Colombia, but I'm not entirely certain on that. I couldn't find the actual location of that to confirm it, but I thought it was such a cool picture. I wanted to include it. It kind of outlines the fact that these volcanoes occur on coastlines. The second type of volcano that occurs, the second type of volcanic zone that occurs because of subduction zones are called island arc volcanoes. Island arc volcanoes. And these are oceanic convergences where one ocean plate dives underneath another ocean plate and produces volcanoes that pop up from below the water surface to form island arc volcanoes. So they're islands, and they usually form in the form of an arc. So they call them island arc volcanoes. Japan is a great example. Japan is an arcing set of islands formed from volcanic eruptions. There are many volcanoes along Japan's coastlines and in the center of Japan. And Japan is basically one big arc of volcanoes. Mount Fuji is among one of the largest and very explosive volcanoes. And you see that picture in the lower right. That's Mount Fujiyama in Japan. And you can see in the picture the tectonics behind this is the Pacific plate and the Philippine plate are being subducted underneath the Eurasian plate here to form the Japanese islands. And you can see it further north even, there's a North American plate soliciting subduction as well. Island arc volcanoes. What was the last one called? volcanic arc volcanoes. Those are ones that occur along the coastline due to subduction zones. The ones that occur and create islands due to subduction zones, island arc. So these are kind of the two major zones where explosive volcanoes form. So you might want to make note in your notes, explosive volcanoes. Andesitic magmas. Andesitic and rhyolitic magmas. Explosive volcanoes. In fact, because of all the subduction that's taking place around the Pacific Ocean, they call that area the Ring of Fire. The Ring of Fire. Surrounding the Pacific Ocean, the ring of volcanoes that surrounds the Pacific Ocean, the Ring of Fire. So much subduction takes place that there's ample volcanoes around all the continental coastlines or volcanic arc volcanoes. And there are also lots of island arc volcanoes, specifically along the west coast of the Pacific there, the Aleutian Islands of Alaska, Japan, we just talked about, the Philippines, Indonesia is thrown in there, even though it's from a different suite, and then the New Zealand Islands, New Guinea, the Ring of Fire, island arc volcanoes in the west, typically, and volcanic arc volcanoes in the east Pacific. Pacific Ring of Fire. We can't forget mid-ocean ridges. Formed at divergent boundaries, mid-ocean ridge volcanoes are probably the most abundant on the Earth's surface. Even though we have that big Pacific Ring of Fire and there's lots of explosive volcanoes there, these non-explosive volcanoes that occur at divergent boundaries are probably more active and more numerous on the Earth's surface. In fact, they are. Of course, the Mid-Atlantic Ridge is an example of this. Iceland is one example that's above the Earth's surface. You're seeing a picture on the lower left from Iceland, and then the lower right as well. This magma is not from melted crust. This magma is from deeper in the mantle, and it rises up to the Earth's surface and splits apart the ocean's crust. And so driving apart the tectonic plates at divergent boundaries is this rising basaltic magma. It's hot, it's runny, it's high in iron and magnesium. It ends up forming thin, dense ocean crust, and it sinks low in the mantle, and therefore that's why it's called ocean crust, because it's usually found under the ocean and paving the ocean floor. Iceland is a exception because there's a lot of basaltic magma coming out of there in a very short amount of geologic time to form a big island there. Divergent boundaries and their accompanying basaltic magma often form, their magma is so runny that they don't form tall volcanoes, they form these big, large volcanic plateaus. Okay, and they're layer upon layer of basaltic magma. It's really runny, so it runs out in a flatter area. And Iceland could kind of be referred to as a volcanic plateau. Areas where lots of basaltic magma pours out on the Earth's surface are called flood basalts because basalt is flooding onto the Earth's surface. And Iceland is a small example. There's actually bigger areas of flood basalt. The Columbia River flood basalts in Washington State in our country. There's one called the Deccan Traps in India. The Siberian Traps in northern parts of Russia. All big, huge plateaus of basaltic magma. Yes. What type of volcano would be the Yellowstone volcano? Great question. Those are hot spots, and that's our last type of environment. Our last type of volcanic environment are hot spots. Heat builds up under one isolated pocket of magma coming from the mantle. A big blob of magma constantly fed by the deep mantle, producing millions and tens of millions and hundreds of millions of years of eruptions, hot spots. Of course, Hawaii is our prime example of this environment. There's a large hotspot underneath the large island of Hawaii. But that hotspot has been feeding volcanic activity on the Pacific plate for hundreds of millions of years. So as the Pacific plate has drifted northward and now northwestward over that hotspot, we have volcanic chains of islands that reach from the large island of Hawaii all the way northwest to the Emperor Seamounts and the Midway Islands. Further north, as we go all the way up to the Aleutian Islands, you can track the hotspot activity from Hawaii. And perhaps an even more infamous hotspot would be the one underneath Yellowstone National Park, which sits in the northwest corner of Wyoming. And right where Idaho and Montana and Wyoming meet, there's a huge magma pocket being fed by rising basaltic magma in the lower mantle. As it melts through the continental crust, it picks up so much silica. By the time it reaches the Earth's surface, it is thick, sticky granitic magma, thick, sticky rhyolitic magma. And as a result, that thick, sticky magma and the enormous nature of this magma pocket produces a volcanic super eruption, a catastrophic type of eruption called ultraplinian that can actually cause the last time it erupted, in fact, it covered the entire western half of the United States in ash, everything west of the Mississippi. The Yellowstone caldera, it's called because it's such a huge crater that's dropped down from the past eruptions, is 26 miles wide. And it erupts every 600,000 years. The last time it erupted, 600,000 years ago. So there is activity under Yellowstone, and they would expect it to erupt anytime in the near geologic currently, right? In the near future. There is surging of that magma pocket producing frequent earthquakes. There's, of course, heated groundwater to produce geysers and hot springs. So Yellowstone is a continental hotspot. Hawaii is a oceanic hotspot. But both of them are examples of the last tectonic environment hotspot. So we had volcanic arc volcanoes, island arc volcanoes, divergent boundary volcanoes, and hotspot volcanoes. Yes. Question, Ian? The near geologic future means tomorrow or 10,000 years. Absolutely. Yep. So when you're talking in terms of geologic time, it's bigger spans of time than, of course, our lifetime is referred to in. Good point. Okay. When you pair our different environments of volcanoes with the different types of magma, I just wanted to give you a visual of this before we end this discussion. You can see on the far left volcanic volcanoes occur from melted ocean crust diving into the mantle. And that melted crust rises to the surface, producing typically andesitic magmas. But you can have anywhere on the spectrum from slightly basaltic to slightly rhyolitic magmas on these volcanic arcs and these island arcs. Ocean islands, that's referring to your hotspots. So typically basaltic lavas near hotspots. Hawaii is an example. You see lots of basaltic magma, basaltic lava that erupts from there. And then basaltic lavas operate at the mid-ocean ridges. Okay, so if we're going to quantify volcanoes, the most volcanoes on the Earth's surface are divergent boundary volcanoes. They're the most peacefully erupting. There are hotspot volcanoes, of course, and then there are island arc and volcanic arc that form above subduction zones. Those are less in number, but more explosive. Lastly, today, eruptive materials. Lava flows are one example of eruptive materials. Since lava flows are so common in Hawaii, They were actually named with Hawaiian names. Two types of lava flows. A slowly cooling lava flow is called pahoehoe, and it's smooth and ropey. It's a fun word to say. And then ones that the lava flows that cool a little more quickly cool in a rough, jagged form, and they're called a'a. And a great way to tell the difference between pahoehoe and a'a is that when you walk over pahoehoe, it's nice and smooth and ropey. When you walk over a'a, you're like because it's so rough and jagged. And then those frequently erupting volcanoes underneath the water in divergent boundaries, they produce oftentimes called these rounded blobs of lava because it's so cold in the deep ocean environment. The lava comes up and it forms these bubbles called pillow lava. So they're called pillow basalts or pillow lava, and that's typically a deposit we see of magma that's risen to the surface, cooled as lava flow, and underneath the Earth's waters. Okay, so hoi hoi and pillow lava are lava flows. And of course, there are uh, volcanic materials from large eruptions. These are called pyroclasts. The word pyro means fire, and clast means rock, fire rock, or pyroclast. There are two types of pyroclasts. There's tephra, which is the small stuff, volcanic dust, volcanic ash. And then larger pyroclasts, lapilli, which are like fish tank rocks, pebbles. Volcanic bombs, which are like baseballs. When a volcano erupts, it actually sends blobs of magma flying through the air. They actually can cool as they fly through the air, and they cool like a baseball with a tail. That would be like a volcanic bomb. And then volcanic blocks are the big stuff, the big blobs that cool, and some of the broken pieces of volcano top when the thing blows. You're seeing a pyroclastic cloud. We'll talk about that when we talk about volcanic hazards. It is a big killer when it comes to volcanic eruption. So pyroclast in the form of tephra or pyroclast, small stuff versus the bigger stuff. And here's a picture of each volcanic blocks and volcanic bombs, and lapilli, the pyroclast, and volcanic dust and ash here as an example of these visually. So that's it for today. I don't want to go any further, obviously. We don't have enough time, and eruptions, landforms, and hazards are their own thing. So we'll talk about those next time. Thanks for listening. We talked volcanic terms like magma and lava, volcano and vent. We talked magma, basaltic, andesitic, and rhyolitic, tectonic zones, divergent boundaries, hot spots, and of course, subduction zones produce volcanic arcs and island arcs. And then eruptive materials, lava flows, pahoehoe, pillow. And we talked uh, pyroclasts and tephra. Tephra is the small stuff, pyroclasts the bigger stuff. We'll talk about eruptions, landforms, and hazards next time. All right, let's talk eruptions. There are really two kinds of eruptions that you can have with volcanoes, and that is either explosive or peaceful. The explosive type creates big billowing clouds of hot ash, gas, and pyroclastic debris. And the peaceful type just squirt magma out onto the surface. We call it lava at that point. It creates lava flows of different varieties. How much a volcano erupts, or depends on the amount of magma, of course. And how violently the volcano erupts depends on the trapped gases. If the magma is thick and sticky, it's likely to have trapped gases. If the magma is a melted magma, it's likely to have trapped gases. Mantle magma, the basaltic type magma, that's usually peacefully erupting. And the melted magma, the rhyolitic and andesitics, explosive. You see a picture of Mount St. Helens on the right. I'm going to talk more about that when we talk explosive. This is 1963 Spirit Lake, beautiful picture of Mount St. Helens. May 11th, 1980, the snow cap is gone. Something's going on here. And in 1982, after the big eruption on May 18th, 1980, you can see a mile-wide horseshoe-shaped crater. The entire top of the mountain is blown off. Because Mount St. Helens erupted in an explosive eruption. It came from melted magma. Rhyolitic and andesitic magma from a subducting plate, the Juan de Fuca plate underneath the North American plate. It produced then melted magma that had a lot of water vapor in it, trapped gases. Another example from an island arc, Mount Pinatubo in the Philippines, 1991, erupted in a very explosive eruption. This is because there was a subduction of the Pacific plate underneath the Eurasian plate, which is why the Philippine Islands are there. They're a giant chain of volcanoes. Now, we won't get into the details about the types of explosive eruptions, and you really don't even need to write them down, but I wanted to at least mention them. Strombolian is when you have a tiny bit of magma that has forms of explosive eruption. It's named after the Stromboli volcano in Italy that does this. Volcanian, usually the initial phase of a bigger eruption, which is called Plinian. These are the main types of explosive eruptions. And then on occasion, when the magma pocket is extremely huge and the eruption really big, you call them ultraplinian. Peaceful erupting volcanoes come from mantle magma. It's hot, it's runny. It doesn't have a lot of trapped gases. It's basaltic magma. Iceland shows this kind of eruptive behavior. Hawaii. And so they call these eruptions Hawaii, Icelandic, Hawaiian, and even flood basalt if there's a lot of Icelandic. Again, don't need to really know those, but I wanted to at least mention them. Here's a picture of Hawaii's Kilauea squirting up a lava fountain. Again, you don't see that big billowing cloud there. It's just lava flows, not a lot of gas there. And peaceful eruptions ensue. Let's look at the resulting landforms. From those peaceful eruptions, you can get flat-lying layers known as a volcanic plateau. These are layers of basaltic lava flows. They come from peaceful eruptions. And of course, we would see them then at divergent boundaries, like Iceland or the Mid-Atlantic Ridge. Iceland is just one part of the Mid-Atlantic Ridge that's particularly voluminous in its magma output. So much so that it created an island of flat-lying basaltic layers. Iceland is a volcanic plateau. If the mantle magma is a little bit more viscous, you might form a shield volcano. This is gently sloping layers. Again, the magma is pretty runny. It's mantle magma, it's basaltic magma, but the layers are gently sloping and they build up pretty tall. Of course, Hawaii is at a divergent boundary, a hot spot. And so the mantle magma that comes up has burned a nice, wide, large conduit through the crust, through the lithosphere and through the asthenosphere. So it's got a constant supply. And so Kilauea on Hawaii's surface is constantly erupting. And as it constantly erupts, the plate is also slowly moving northwestward. And so you create a chain of islands from these shield volcanoes. So the Hawaiian island, the large island of Hawaii, and all the rest of them are shield volcanoes. If you followed them up northwestward and then northward through the ocean, they're all shield volcanoes. And they call them shield because they look like a medieval shield from the side, like a knight would set his shield down and it would be gently sloping. Cinder cones are built up cinders around the volcanic vent in the shape of a cone. That's why they call them cinder cones. Cinders are lapilli. They're the baseball or the fish tank sized rocks that get erupted from a volcano. These could be Rhyolitic, andesitic, or even basaltic in some cases. They're like little mini explosive eruptions that come out of here. And oftentimes the magma will make its way through the existing cinder as it erupts. And then when it stops erupting, it'll cool off, forming a volcanic neck. So the cinders, they eventually wear away, and left behind is this igneous volcanic neck. And igneous rocks that cool underground are chemically interlocked. They're way more resistant than those cinders. So even when the cinders wear away and erode away long after the eruption, remaining will be that volcanic neck. Famous volcanic neck? Devil's Tower in Wyoming. Devil's Tower in the eastern part of Wyoming is part of that Black Hills magma plume that came up and rose the crust up, and it formed a big volcano there. And the volcano, the material cooled, the magma cooled inside of that volcanic neck and formed these big hexagonal columns of granite. This is a really neat place to visit. One of the beautiful places on the Western U.S. bucket list of things to see. They occur near convergent boundaries, but they can be hot spots like Devil's Tower and the Black Hills as well. And stratovolcanoes. They call them composite cones because they're a composite of both lava flow layers and erupted material. So they form stratum or layers, so they're called stratovolcanoes. These are your explosive type volcanoes. You get this melted magma, the andesitic and rhyolitic magmas that rise to the surface and explode out in these big billowing clouds, raining down pyroclasts. And then after those kind of settle, the lava flow, the last bits of lava that come out kind of flow down the mountainsides and build up these, and it's pretty thick and sticky magma, so it builds up these steep slope volcanoes. So whenever I say the word volcano and ask you to picture it in your mind, you're probably going to picture a stratovolcano, steep-sided, symmetric cone with a snow cap on top. Beautiful example here in the lower left, Mount Fuji in Japan. Mount Fuji, or Mount Fujiyama, is the largest stratovolcano in Japan. It's one of those beautiful snow-capped volcanoes. Of course, these convergent boundaries, island arc volcanoes, volcanic arc volcanoes, these are stratovolcanoes. Mount St. Helens, stratovolcano. Mount Vesuvius, stratovolcano. One more volcanic feature, and that is a caldera. If your magma pocket is enormous and the eruption is a ultraplinian eruption of that magma pocket, tons of billowing material over a huge area, the eruption is going to be extremely large, catastrophic, colossal. After all that stuff erupts, there's a void in the ground where it once was in this huge magma pocket. The area will then drop down to fill in the void. And so you're left with this enormous crater, miles wide. Yellowstone is a prime example of this. The Yellowstone caldera is 26 miles wide. So a caldera is a large volcanic crater left behind by a super eruption. I have an example here on the slide. The lower left, you see Crater Lake in Oregon. Beautiful lake formed from a violent eruption. This was a ultraplinian eruption that left a stratovolcano, Mount Mazama. It blew its top. It completely blew off the top part of the volcano, leaving behind, after the eruption, this big divot in the center of the volcano, now filled with water. There was a little minor eruption from this caldera afterward, thousands of years afterward, called, and it's now called Wizard Island. So that's what that little island is in the center, little volcanic dome. But Crater Lake in Oregon is an example of a caldera atop a stratovolcano. An example of a caldera on the continent is Yellowstone. Yellowstone National Park, as I said, has a caldera that's 26 miles wide, a drop down area from the last eruption, which was 600,000 years ago. And here's Yellowstone in the United States, right here in the northwest part of Wyoming, where Idaho and Montana meet Wyoming. And Yellowstone is atop a hotspot. This is a nice open conduit of mantle magma, basaltic magma coming up, but it has to burn its way through continental crust. It picks up lots of that low density silica along the way, becoming a rhyolitic magma, an explosive magma. And this stuff is continuing to pool up and pool up until it reaches its tipping point. The area above it is shifting and moving, causing frequent earthquakes. They're magmatic earthquakes because that magma pocket is shifting and surging underneath. And it's heating the groundwater, causing beautiful hot springs and geysers. Yellowstone, again, another one of those places on the bucket list of beautiful things to see in the country. I just hope you're not there when it explodes. It erupts every 600,000 years, and it erupted 600,000 years ago. That's why we see so much activity there. And here it is, the most current eruption with the hotspot track moving all the way across the southern part of Idaho. There's a beautiful state park here called Craters of the Moon State Park, or National Park, that is, in Idaho, southern Idaho. That's part of that Yellowstone suite. Yes, Ian. Great question. So we know that there's big slabs of tectonic plates on the surface of the Earth, right? Why do the plates move the motion they do? Because there are some plates that are diverging because of spreading centers. Other plates are subducting, kind of dragging the rest of the plate with them. And there are transform slippage as well. Because these boundaries are not like perfectly square, each plate is going to move in its own kind of like asymmetric way to respond to all the activity from the magma pushing it around. That's right. The asthenosphere is constantly convecting rock. There's constant magma escaping to the surface at those spreading centers, so the plates push up, and then gravity pulls them down. Subduction pulls the plates down, and bada bing, bada boom, you got motion. Yeah, and it's really hot in the asthenosphere, and it's really cool at the surface. And thanks to Earth's water supply, and 75% of the Earth's surface covered by water, the water creates not only a lubrication for the plates descending, but it also creates a situation where it's nice and cool for the temperature difference of the surface versus the hot interior. Rock is constantly convecting and moving. So our plates are constantly moving and grooving. Great question and topic. Let's end today with hazards. The hazards of volcanoes are things that kill and destroy. And there are really two main hazards. There are others, but we're not going to really kind of focus in on them here in this class. Take natural disasters if you want to hear more. First one is pyroclastic flow. That big billowing cloud of hot air, which is mostly water vapor gases, ash and dust, the tephra, and the pyroclast, that thing is heavy. It's a rock cloud. And that billowing rock cloud goes upward, but it also crashes down and goes outward oftentimes. And anything in its path, when you get hit by a rock cloud, you can kind of imagine what would happen. It's going to blow everything away and burn everything away. This is called a pyroclastic flow, a fire rock flow. These, of course, come from explosive eruptions, mostly from stratovolcanoes. This is melted magma fueling this, rhyolitic and andesitic magmas. And you see a picture montage of the eruption of Mount St. Helens here. So Mount St. Helens was showing signs of activity, so it was heavily monitored. And they had cameras set up on the volcano. So when it erupted, They got great pictures of it erupting. So what we saw was that the mountain started bulging on its side. That caused a landslide, and the landslide let loose the pressure of the rock on the magma below, and it blew out. It blew upward, and it blew outward to the side. And as a result, it caused a pyroclastic cloud that wiped out much of that area on that side of the mountain. Another example of a pyroclastic situation was the eruption of Mount Vesuvius. This is in Italy, on the west coast of Italy, and it buried the city of Pompeii in a pyroclastic flow. These people had this big billowing cloud rush through their city. It blew things down. It basically encased people in volcanic ash. And scientists later, or archaeologists later, went through and excavated this site and found the people and their buildings and everything. And I think it's another place you could go visit as a tourist and see the raw power of nature and the poor fate of these people. The crazy, and you can see Mount Vesuvius in this picture. The entire top of the mountain blew off in that eruption. They thought it was an extinct volcano before it just completely blew and wiped everything out. The crazy thing about this is Mount Vesuvius today. Look at the population. That is Naples, Italy. 3.5 million people live there. In my mind, that's kind of crazy that we settled this killer volcano so heavily, but it's there. So, very interesting. Pyroclastic flows. A second deadly event that comes from a volcanic eruption, lahars. Lahars are volcanic mud flows. So if you don't get hit by a big billowing cloud, you have to stand the potential of being wiped out by a large landslide, a mud flow, mud cascading down the volcano sides like um, a wall of water. What happens is the snow-capped stratovolcano has the volcanic dust and ash mixed with it. It melts it, and they all roll down together, and they go blowing down the mountainsides, down the valleys. Oftentimes, people live in river valleys on mountains because they provide fresh water, uh, source of food, and so forth, transportation. And so that's where the mud flows come. This is a picture of Soufrière Hills, the Montserrat, Martinique, and a resulting mud flow. It made kind of a good picture of what mud flows end up looking like in buried areas. These again come from your melted magma, explosive eruption, stratovolcanoes, island arc, volcanic arc situation. There was an infamous mud flow in 1985. It was from the Nevada del Ruiz volcano in Armero, Colombia. Armero, Colombia had a population of 27,000. After this eruption and ensuing lahar, 23,000 of the 27,000 people were killed. You can see the map in the lower left showing that Nevada del Ruiz is one of a series of volcanoes in Colombia along the coastline. Again, this is a volcanic arc. It's the northern volcanic arc in South America from a subduction zone. These are melted magma volcanoes, stratovolcanoes that cause pyroclastic flows from lahars. The picture in the upper right shows Armero before and then Armero after. And it was a real big humanitarian disaster. Many people and their things were buried in mud. You can see by the picture in the lower right, it was really a terrible thing. So those are volcanic hazards. So today we talked eruptions, landforms, and hazards. And the broader topic of volcanoes, looking at the terms, the plumbing associated with volcanoes, the creation and types of magma, the tectonic zones, and our eruptive materials, and in addition to our quiet, peaceful eruptions and our explosive eruptions, our resulting landforms of plateaus and shields or cinder cones and stratovolcanoes, and then again calderas, and then finally pyroclastic flows and lahars. So thanks for listening. I hope you enjoyed volcanoes.